So maybe we can start. So I'm glad to announce the winner of the AILA Prize 2014. It is a triennial prize for PhD thesis on mathematical logic and similar topics. Let me recall some recent winners of this prize: Giovanni Curi and Sonia L'Innocente in 2005, Tamara Servi and Giuseppina Terzo in 2008, and Olivia Caramello in 2011. This year, the participation to the prize was very, very large, and according to the committee, the level of the thesis presented was very high. So I want to name all the participants before announcing the winner. Federico Aschieri from Turin, Dario Dalla Monica, Udine, Umberto Grandi, Amsterdam, Giorgio Laguzzi, Vienna, Lorenzo Luperi Baglini, Siena, Vincenzo Mantova, Scuola Normale Superiore Pisa, Fabio Pasquali, Genova, Andrea Predrini, Milano. I think a cheering for all participants. Thank you. The committee was consisted in Stefano Baratella, Trento, Antonio Di Nola, Salerno, Paolo Lipparini, Rome, Simone Martini, Bologna. And the winner you all know who is the winner since it is written there. So, but I prefer to read the motivation, the its appreciation topics covered and their interdisciplinary nature. The committee unanimously decided to award the prize to Dr. Vincenzo Mantova for the thesis Zilber Fields and Complex Exponentiation for the following reasons. The proof of existence of an involutive automorphism of Zilber's exponential field proposed by Mantova is ingenious and technically complex. It answers positively to an open question lasting for nearly a decade in modern theory and provides an indirect argument in favor of an important conjecture in the theory of transcendental numbers. So I would like to invite Vincenzo Mantova, who is already here, and the president of AILA to give the prize.
I have to say that AILA recalls a series of detective stories in TV. So AILA is better, in my opinion. Yeah. However, I have to say that in the past, the AILA Prize, AILA Prize, if you like, consisted of our hospitality during the conference, so lodge, food, accommodation expenses, and also book. but it was impossible, I guess, to fund in Pisa all that for Wiener living in Pisa, and so we preferred, we agreed that to offer to Vincenzo, our congratulations of course, and the whole series Matematica of Scuola Normale Superiore, including Logica dimostrativa of Gerolamo Saccheri, Euclide vendicato da ogni neo. I do not remember the Latin originary title. Euclides ab omni lembo vindicatus, I am not sure. Also by Gerolamo Saccheri, and then the Logica Matematica book edited by Gabriele Lolli, and also another book, not of Logica, I guess, but this is our prize, and we hope it will be okay, will satisfy you instead of lodging and food expenses. So congratulations. Abbiamo messo tutte le firme.
So now Vincenzo can illustrate his work, his thesis.
Thank you. Oh, it's working. Okay. Amazing. Okay. Well, thank you very much for the nice speech. Thank you to Aila, to the committee. Thank you to everyone for being here, and thanks to all the people who actually gave me a job in the last years. So the Scuola Normale for the PhD project, the PRIN, o minimalità, teoria degli insiemi, eccetera, the Zilber, nuovi sviluppi nella teoria dei modelli dell'esponenziazione, the Maloa project, who found me for a while. Okay, I think I did mention everyone. Okay, so what I'm going to talk about is really about my thesis, but it's also about the context in which this work was done. Okay, so the main issue now is talking about the exponential function, which of course I think all of you know what we are talking about. So the exponential function has several definitions. So for example, you can say it's the function given by this convergent power series, and well, it has a lot of nice properties. So it's a very special analytic function. So the first equation that you write down usually about the exponential function is that the exponential of z plus w is equal to the product of the two exponential of x of z times x of w. And you can also say, for example, that it is the universal, it's the map, universal covering map from the additive group of the complex number to the multiplicative group of the complex numbers. Or you can say it's the solution, the unique, well, up to a constant, it's the unique solution to this differential equation. And for example, you can say that the exponential function has this nice property, it commutes with complex conjugation. The exponential of the conjugate of z is the conjugate of the exponential of z. So this is all like some easy properties about the exponential function. Now the point, and well, I just mentioned right now that using this property here, the exponential function commutes with complex conjugation, you can actually decompose the function on the complex number into three real functions. In this way, there's e to the x, which is the real exponential function, and then there's the trigonometric function, cosine and sine. Okay. And then there's other exponential functions. So I should mention this. For example, on the p-adics, you can use the same, well, not exactly the same expansion, but essentially this one to define an exponential function on the p-adics, because you have a topology, and then you can talk about convergent power series as well. And then you have similar issues, but they were explained in another talk. So I will talk about this one. So now the thing is that when you look at this decomposition, then you can... What? Oh, on the first slide, amazing, thank you. Okay, so let's start. Well, actually this e to x and the cosine and the sine function are somewhat different. So if you study the real exponential function, then you have a really nice, this is a really nice function. So this is a really fundamental theorem about the theory of real exponentiation that says that the first order theory of Rexp is model complete and it's actually minimal. Okay, by Alex Wilkie. And there's even more. You can even prove that assuming Chandler's conjecture, which is going to be the subject of the next slide, then actually the theory is also decidable. So you have an algorithm to say if a formula is true or false. Okay, but and actually Chandler's conjecture is like one of the main topics about the exponential function. So this is Chandler's conjecture. It was stated in its full form. It was stated in the 60s. Okay, and it says that if you take n complex numbers at 1 z n, okay, if you assume that there is no linear relation with rational coefficients between these numbers, then the transcendence degree of z1, zn and their exponentials is at least n. Okay. Well, this is just a rough sort of motivation for this conjecture. The idea is that, of course, if you have a relation like this one between z1, zn, okay, which is one algebraic relation, then where these coefficients, well, they should be rational since there is q here, but of course we can assume that there are integers. Then this algebraic relation induces another one. Oh, there's another typo. Another relation here, e to z1 2m1 times e to zn 2mn is equal to 1, not to 0. Okay, so that's another algebraic relation. So, and Chandler's conjecture is saying that if you have many algebraic relations between these values here, then there must be one of these easy relations, because they are able to produce two relations at once, just because of the fundamental equation of the exponential function, which must be an homomorphism. Okay, and well, you can use it to prove, like, see, if you assume Chandler's conjecture, then you know lots of stuff about the transcendence of the values of the exponential function. So, for example, it's almost immediate to see that the e is transcendental. That, for example, if you take e of square root of 2 and e of square root of 3, they are algebraically independent. Log 2 is transcendental, and for example, e and e to e are algebraically independent, or the same for log 2 and log 3. Except you see that these results are well known, and actually they've been we are quite old. While these ones, we really don't know anything about these examples here. So we don't know if log 2 or log 3 are algebraically independent, for example. Okay. Okay, now the point is trying to study the full exponential function, not just the real one, but adding also the trigonometric function and study the full exp. Okay, and well, there's now you have problems. You immediately have one problem, one which is easy to overcome, somewhat easy. So first of all, the kernel of the exponential function is 2 pi I z. So the first thing you can say about 2 pi I z, at least it is an infinite discrete group. So certainly, if you want to study, if you try to study the structures on the real numbers, so you really split this function into a real exponentiation, cosine and sine, then you cannot have a minimality, for example. Okay, you cannot define this object here. But then this part of the problem, the fact that this kernel is this infinite discrete group, is by itself is not, well, it's a relatively small issue, in the sense that Zilber managed to show that if you study this structure here, where the exponential function is just an abstract cover of the multiplicative group, okay, so it's an homomorphism from H to the C star, and H is just a divisible, torsion-free abelian group. Essentially, it's something which looks like the additive group of the complex number, but it's not the additive group of the complex number. It's just an abstract group. And you have the kernel is the ring of integers. Then you can find this an axiomatization in this infinitary language, okay, which is uncountably categorical. Okay, this is a way to overcome this obstacle. Since you have this group here, which is not stable, it's not omega it's not omega stable. So you can certainly, this is not a categorical structure in the sense of first order theory, unless you go to this stronger language. In fact, you use this N omega 1 omega, which means infinite, essentially just infinite countable conjunctions, and these junctions to write this sentence. That an element is in Z, in the sense it is in the kernel of this function, exactly when it is a finite sum of 1 or minus the sum. I mean, this means this is really the group of the additive group of the integers. You don't admit, there is no standard model of this part, because you really capture it with this sentence. And in this way you can find this axiom, which of course it's an infinitary language, so you don't have all the nice properties of classical first order model theory. You don't have compactness theorem, so essentially it's different, but still you have nice properties, which I will explain a bit more in detail later, because you have the class of models of this sentence form an abstract elementary class, and more precisely they form a quasi-minimal excellent class. So they have nice properties. Okay, now the true problem, of course, I think you were also thinking why he is not saying this. It's that actually you can define the ring of integers, okay, inside the complex numbers. And since the exp is actually mapped from the additive group of the complex numbers to the multiplicative group, you have that Z is definable there, and then you can just you have multiplication on C, and then you have a ring, the ring of integers, and then this is not well, interprets Peano arithmetic, so it's undecidable, not stable. Okay, so that's really, you cannot do this, you cannot study this using the stability, the usual, I mean, stability theory in the sense of stable to super stable or minimality, etc. But the idea is to look for other kind of tameness about this definable set. So, for example, Zilber conjectured first that the structure of complex exponentiations should be quasi-minimal. Quasi-minimal means that every definable set of C, subset of C, should be either countable or co-countable, which is just in analogy for example, with strong minimality. So if you take the complex field, this was mentioned yesterday, if you take the complex field without any, just with the field structure, but with no exponentiation, every definable set is either countable, is either finite, or the complement is finite, and that gives you lots of nice properties, because then you have this algebraic closure operator, which in the case, I mean, for an algebra, for C, which is an algebraic closed field, we're really talking about algebraic closure, which has nice properties. Okay, and then Zilber conjecture, I mean, something similar maybe happens for complex exponentiation. And the problem is we don't know the answer to this question. And at this moment, it's even possible the complex exponentiation is able to define the real line inside the complex field, in which case that's certainly not quasi-minimal. Okay. But then now the problem is also still about Channel's conjecture, because we want to understand, if you want to understand the algebraic behavior of exponentiation, at some point we would need to talk about what happens here. Because, for example, this is just to recall the statement and also some consequences. For example, Schaunel's conjecture implies that pi is transcendental, but we know that pi is transcendental. It implies that e to pi and pi are algebraically independent, which is actually not so easy result in transcendental number theory. Actually, quite recent as well. Then it would imply also that e and pi are algebraically independent, but we don't know this. Okay. Okay, now Zilber's idea was to just say, okay, we don't know much about Schaunel's conjecture. Okay, but let's see what happens if we assume Schaunel's conjecture. We start using Schaunel's conjecture but just in an abstract setting, forgetting for a moment about complex exponentiation. Okay, now I'm going to be more technical. Okay, so let's say that let's just start just thinking about abstract exponential field, which means we just take a field k of characteristic 0. Let's avoid in other situations, and keep with a function. And at the beginning, we just ask that this function is an homomorphism for the additive group to the multiplicative group, so it satisfies the same fundamental property of exponentiation. Okay. Now, this function at this point, this function could be even trivial. You could just send all the field to 1. It would be an homomorphism. Okay. And then we could just require that this function must satisfy the statement of Schaunel's conjecture. Okay, so we really require if you take n numbers in the field k that are q-linearly independent, then this transcendence degree is at least n. Okay, we start with this property. Okay, and then we have to do something a bit more complicated. Okay, we actually restrict our attention not just to the fields with this property, but we also require that the kernel of the exponential function is really a cyclic group. It's just like 2 pi I z. The kernel is omega z, where omega is some non-zero element of the field k. And, well, now this is more complicated. The point that I want to make here is just that let's just take the finitely generated fields with this property. Now, finitely generated is a bit, you have to be careful because it depends on which language you're using. So, for example, actually I need to use partial exponential fields, which means just that the function is not defined on the field k, just on a subset of k, while having always this property and Schaunel property, etc. Now, what happens, the nice thing that happens in this case is if you look at this finitely generated field, then they amalgamate. They have the amalgamation property. Except you have to be careful here. You have the amalgamation property, but you have to add the restriction on which kind of embedding you allow here between the structures. So you take these finitely generated structures, if this one embeds strongly into this other exponential field and this other exponential field. What strongly means, I won't say exactly what it means, its meaning is just that it plays nicely with this inequality here. So it doesn't mess up with the descendance degree of the values of the exponential function. Let's just say in this way. Well, when you use strong embeddings, then actually we have amalgamation here between these finitely generated structures. Okay, what happens when you have amalgamation? Well, we can take the limit structure of all the finitely generated exponential fields of this kind. Okay. Now what happens is there are just countably many isomorphism types for this structure, so the limit here is just like the usual Frasse limit, except in this case it's the Ruszowski-Frasse limit because there's this strong embedding talk which was actually invented by Ruszowski. And the object you get here is a countable field which contains a copy of all the possible finitely generated exponential field. And this object here is a Zilber field. It's a countable Zilber field. So this is an example in the countable case. Okay, and then if you want to make an axiomatization, then you can, well, certainly, for example, you can start by studying this structure. and seeing which properties it has, and then Zilber came up with this list of axioms here. Okay, now the first one, well, the field must be algebraically closed, for example. Why? Because it must contain, certainly it must contain all the possibly finitely generated fields of characteristic 0, and then for this reason it must be algebraically closed. Then you can see that, of course, this function E on the field must be an homomorphism from the additive group, just because every finitely generated substructure has this property. Its kernel is always omega z. And then, since every finitely generated substructure satisfies the Chandra property, then the same statement is true on this limit. And now this is the tricky part in some way. This is a bit difficult to state properly. But let's just say that all the systems of polynomial exponential equations which are compatible with the Chandra property, well, then if they are compatible, then they have a solution in the field. And the reason is, well, compatible means that there is at least one exponential field with the Chandra property where this is true. Okay? But this field must contain all the finitely generated exponential fields. So certainly it contains a copy of the field where there is a solution. Okay. And this is what you get. These first axioms are what you get just if you can get them just by thinking about the previous picture about making this limit. Now the last one is well, is more delicate. Is about what happens when you don't want just countable Zilber fields. You want Zilber fields, so larger cardinalities. And then you have to put this restriction that when you take this exponential algebraic closure of finite sets, then you must get countable sets. Okay, you have to put control. Exponential algebraic is something really related also to, obviously, to this property. There are certain system of equations which pick out these exponential algebraic numbers, and then you want this exponential algebraic closure not to be too large. If you start from a finite set, you get a countable set. Okay, and Zilber proved, and this is already not trivial to say, that these properties are axiomatizable again using this language L omega 1 omega, and you use L omega 1 omega again because you want to fix the kernel of the exponential function. You don't want to have no standard model of this z here. This one must be fixed. So you use L omega 1 omega. But then you need an extra quantifier q because you have this condition where these sets must be countable. So you need a quantifier to say there are no more than countably many solutions to certain system of equations. Okay. And of course, the big theorem by Zilber is actually that the sentence expressing those properties is uncountably categorical, which means that the sentence has models in any infinite cardinality, and two models of the same cardinality, of course, are isomorphic. Okay, and this more, I mean, these models again form an abstract elementary class, which is again similar to the one for the case where we just saw the XPath, the universal cover of the multiplicative group. So you still get a quasi-minimal excellent class. And well, to be a bit more, to give the flavor a bit more about this quasi-minimal excellent stuff. The point is that once you're inside this Zilber field, you have a concept of exponential algebraic. So you can define an exponential algebraic closure operator. Okay, and the exponential algebraic closure operator behaves in a way that is very similar to algebraic closure in algebraically closed fields. Okay, so for example, if you take inside the complex number, if you take a maximum number of algebraically independent elements, these T1, T2, T omega, etc., and you take their algebraic closure, then you get the complex numbers, the field of complex numbers. And then C is isomorphic to the algebraic closure of 2 to the aleph 0 algebraically independent elements, whatever they are, because when they are algebraically independent, then they are indiscernible. Okay, they all have the same type. And the same happens for the Zilber field. If you take a maximal subset of exponential algebraically independent elements, then the Zilber field is this exponential algebraic closure of these elements. And then you can just work in an abstract way, take 2 to the alpha 0 exponential algebraic elements. You can make their exponential algebraic closure and you get the Zilber field. Okay. Now, just to say something more, but this slide is really full of definitions, but which are not useful for the next ones. I will just say that these are the properties that must be satisfied by this algebraic closure operator, in this case exponential algebraic closure. So for example, here on this line, here what we say is that if you start with 2 closed subset of a Zilber field, say of a Zilber field, countable and closed, if you take 2 elements which are not inside these 2 sets, so they are transcendental over this H and this H prime, then they have the same quantifier free type over H and H prime. Like in algebraically closed field, if 2 things are transcendental over a set of parameters, then they have the same type. Okay, so there's a unique transcendental type here. And there's some other properties, and when you put them all together, then you have this theorem that says that if you take the class of all the some structures with these properties, with close embeddings, well, I won't say all the details, but essentially you can prove that these properties here are what give you categoricity. Okay. Now there's an issue about excellence, but let's just skip over there, because there was actually a mistake in the original paper by Zilber, but then people realized that it was just because Zilber was proving too much. Excellence was actually redundant in this case. So the theorem was true, but the proof was exceeded. I mean, was trying to prove really too much. Okay, so let's go back now to the issue. I mean, we have Zilber fields. What is the relationship with complex exponentiation? Well, the point is now that Zilber said, okay, we have this sentence. The models of this sentence are a quasi-minimal excellent class. They have a nice model theory, and they are uncountably categorical. So the unique model of cardinal power 2 to the alpha 0, well, it should be complex exponentiation. Why should there be 2 different exponential fields? So natural. Okay, but then of course this is a really strong conjecture, because if complex exponentiation is a Zilber field, then of course it means that Schaunel's conjecture is true. At this moment we have we don't know very much about Schaunel's conjecture. There's no this moment it's we don't believe that you can prove it in the next decades probably. And actually Zilber's conjecture at this moment is even stronger, because if you look at the statement, okay, the axiomatization, okay, you have the Schaunel property here, but then you have also this new statement, which is this strong exponential algebraic closure, which is not known for complex exponentiation. I mean, this may be easier than Schaunel property, but at this moment, if you want to prove Zilber's conjecture, essentially you have to prove that these 2 statements are true on complex exponentiation. Now the third one here is always true, is true. Cx but it satisfies this extra statement here. And of course, it satisfies the first properties. Okay, it's an algebraically closed field, the kernel is 2 pi I z. Okay. Okay, so now the work we are doing, and several people are doing, is comparing complex exponentiation and Zilber fields to see if there is a way of distinguishing them, or to gain some insight on the conjecture. So for example, there are works which transfer some result which are known for complex exponentiation to Zilber fields. And for example, there's this statement, and so it's called Schamless-Nullstellensatz, which was proved using some deep tools from complex analysis, which says that if a function defined using polynomials and the exponential functions with iterations, if this function has no zeros on the complex numbers, then actually it's the exponential of another function of the same shape. So we know it's the exponential of some other holomorphic function, but this is stronger. Okay, and if you want to prove it on Zilber fields, what's the point here? Is that on Zilber fields, the definition of the exponential function is completely algebraic. And since this statement actually is algebraic, then what happens is that it's even easier to prove it here. So you have an advantage. And then this other works, and then, for example, there's we can prove that there is something similar to complex conjugation on the E, which is an automorphism of order 2, which plays the same role of complex conjugation. So on the Zilber field, E of the conjugate of a number is the conjugate of the exponential of that number. Okay, this is what I'm going to talk on in the next slide. And then, of course, then you can try to move in the other way. There are some results of this kind. If I try to understand more about complex exponentiation, starting from the properties of Zilber fields, and you can also do the same assuming Schamless conjecture, which is about and this kind of work, I would say, it's mostly about proving that Zilber's conjecture is actually just Schamless conjecture, proving that the extra properties, the properties that you have here, you can prove them on CX assuming just Schamless conjecture. Okay, but there's also, I mean, there's really a huge amount of other works about which is related always to this kind of arguments, mostly about Schamless conjecture, maybe less about Zilber fields. So, for example, there's nice works about the raising to powers function, which sends it is a function that sends x to tau, where tau is a fixed number, real or complex. It depends on which one you want to study. And this is a function that you can define using the exponential function. Okay, but if you take the reduct, if you forget about the exponential function and just keep this x to tau, then you have nice properties. For example, in this case, now we know that the statement of Schamless conjecture, which we just talk about this function, is true. For example, provided with restriction on the number tau, and then you can study this structure, and this structure you get some statement that are unconditional, not depending on Schamless conjecture, for example. But then, sorry, I'm not going to talk about this. Okay, because now I would like to talk about this problem, about finding, essentially finding complex conjugation on Zilber fields. Because the point is that while on complex exponentiation the definition of exp is done using the topology, is either with a convergent power series, with a differential equation, you always use the fact that you have the Euclidean topology on the complex numbers. So what we would like to find, at least inside the Zilber field, is a real line. Okay. And what should this real line do? Well, if you want to say some basic properties, well, the real line is the fixed field of an automorphism of order 2, which is another way of saying that the real line is just, if you take the algebraic closure of a real line, you obtain everything. Of course, you don't want a small real line. You want to get almost everything. You have this real line in the complex series is complete and Archimedean, okay, and the exponential function is continuous with respect to this topology, and the exponential function commutes with automorphism sigma, commutes with complex conjugation. So complex conjugation is an automorphism of Cexp. And what happens is that if you put these properties, you can use these properties essentially to define complex exponentiation, because there's actually a unique function which commutes with complex conjugation, which is continuous. Well, that's all. Which is continuous and an homomorphism from the additive group to the multiplicative group, up to multiplication by some constant. So what happens is if we find an automorphism like this one with all of these properties, then actually you prove the full conjecture. Okay. So of course, I'm not going to say that we proved the full conjecture, but at least we managed to show that yes, you can find automorphism of order 2 on these Zilber fields, but not such that the exponential function is continuous. This is important. Unfortunately, this part doesn't work out very well. Okay, but you still get an automorphism of order 2, and its fixed field is actually just really isomorphic to the field of real numbers, so it's complete and Archimedean. And no, okay, no, that's a good point. I mean, I did a construction, and the result of the construction is this picture here. I mean, there is a Zilber field and there's an automorphism, and after this construction, the function is not continuous. Cannot be continuous, because the construction, I had to use some tricks to get around a few obstructions, and then it doesn't, the result is not continuous. But no, it doesn't say that if you take any automorphism of the 2, then it must not be continuous. I mean, the conjecture may still be true. Okay. Yeah, I hope that this is just like a byproduct of the way the construction is done. And well, because the construction in some ways is even quite explicit. So how do you obtain this object here? Well, actually, you start with complex. You start with complex conjugation. Okay, there's no exponential function at this moment. We really start with the complex number and with the complex numbers and with complex conjugation. Okay, so we have an automorphism of the field of order 2. And then we construct the exponential function of this field. We define it just really by back and forth. We want a function from C to C star, so we pick an element in C. We take something in C star which is not already in the image of the function, and we just define E. We say that E must send this point to this other one. Okay, and then while we do that, we have to be careful. Well, first of all, we want to have this property. We want to have the exponential of the conjugate of a number is the conjugate of the exponential of the number. Okay, so it means just that when you define E of a number on number Z, you are forced to define E on the conjugate of this number. So you have to be careful, for example, so that the definition is well posed. Okay, and while you do this construction, then you can just say, oh well, I will just force this function to satisfy all the properties of the Zilber fields. Okay, well, if you manage to do this, then the limit of this construction is just a field satisfying the axioms of Zilber fields, because we just made it so. And since the function commutes with complex conjugation, well, then complex conjugation is an automorphism. Okay, so we get this. We get to this, and of course this is not quite easy. I mean, you have some big problems about the fact that in Zilber fields you must have solutions to all possible system of equations which are compatible with this Schauner property. Okay, and that's not trivial. You have already this problem. So let's say that we start with this system of equations. So we have two equations and two variables. Okay, in a Zilber field, this system of equations has a solution. Okay. However, now assume that we already proved that. Assume that there is an automorphism of the Zilber field which commutes with, which is of order 2, which is complex conjugation. Okay, then you can decompose the function E as a real exponentiation and then a cosine and a sine function. Okay, so you can just split. I mean, you take these two complex numbers. Let's say that we were working on C, no, not on B, just really on the complex numbers. You take the real and the imaginary parts of these numbers and you write down, you plug them into these equations, and then you expand them, and eventually you get down to 4 equations in 4 variables. Now with where the variables are over the real numbers now, not the complex numbers. Now the problem that this is a new system. Now at first it's even possible that this new system is not compatible with the Shannon property. So if this happens, if this is not compatible anymore, then this shouldn't have a solution in the Zilber field, because otherwise the Shannon property would be false, more or less. Okay, now okay, I was hoping, in fact I was hoping at a certain point to get to this. I mean, I would say, okay, let's say that they have an example, then probably Zilber's conjecture is false. But no, actually the combinatorics of this system of equations is sort of transparent to this problem of conjugation. If you do this transformation from a system in complex variables to a system in real variables, then the new system is still compatible with the Shannon property. So it doesn't refute Shannon's conjecture having this kind of situation, the Shannon property. And so what happens is that you certainly are able to construct an exponential field with this automorphism of order 2, complex conjugation, so you can do this on the complex numbers, and you manage to construct a field which satisfies the Shannon property, and all system of equations have solutions. You can just add them one by one. You just enumerate all the systems and you define the exponential function in this way. Now what's more difficult to do is that we have to check how many solutions we have on these systems. Because the problem is that every time you define the function on a new point, then some system of equations are going to get new solutions, possibly, because you just you expand the domain of the function and then you can get something new. The problem is that one of the properties of Zilber fields is that the exponential algebraic element over a finite set must be countable many, which translates to the fact that when you take a system of equations of a certain form, of certain shape, which is the word, the system of equations picking the exponential algebraic elements, well, those system of equations should have only countably many solutions. So you have to be careful about what happens. When I define the exponential function on this point, then I have to see where all these new solutions are appearing and to check that this happens only countably many times for each system of equations. And you can do this. You have to really control what is the shape. When you start from a system of equations in complex variables, you translate into a system in real variables, and you have to check to say as much as possible about this new system. And what happens in the end that you can do this, and you can do this such in a way that once a system of equations has countably many solutions, then it doesn't get any more. Once the system of equations has all the solutions that it needs, then you don't have to add any other stuff. And so you can really go on with this construction. You define this exponential function, and in the end you get all these 3 properties here, which are the 3 properties that were needed to say that this resulting field here is a Zilber field. Okay, and that's where you get to the end. And then studying the system of equations, you can do some other weird, define some other weird exponential field, such, I don't know, an exponential field which is similar to a Zilber field and to complex exponentiation in the sense that the kernel is again omega times z, and all the system of equations has solutions, but the ground field actually is the field of algebraic numbers. So the Shannon property is false. Really, if you take the transcendence degree of some numbers and their exponentials, it's going to be 0 because you're just inside here. And you can recover if you sacrifice some of the axiom of some part of the axioms of Zilber fields. You can construct some better exponential fields. For example, you can make sure that you still have an automorphism order 2, and on the fixed field, which is real closed, then the function E is increasing, is an increasing function. But then, well, I managed to add solutions only to the one variable systems, not to all of them. So there's the restriction. And well, and then the problem is that with what I was saying before, with this construction, what happens is that to get around some problems about discounting of the solutions, at a certain point I use a trick just to say, okay, this set of solutions on a system of equations, they should be dense, so sparse, really dense in the sense of the Euclidean topology, I mean with respect to the ordering of the real numbers. That means the exponential function cannot be continuous, because it should be a discrete set, but it's dense. That's why with this construction you don't get that the exponential function is continuous. But then the problem, I mean, I would say that the problem is mostly because I didn't say enough about what happens to this system of equations. There are some things that if you manage to prove more, then actually you can get around this problem, then hope that maybe you can get a continuous function. But, well, I don't know, I mean, there's work to do. Okay. Thank you. Oh, I mean.
Function changes sign and has a root.
Oh no, one variable. No, I mean really. No, what I really mean is p of z e to z equal to 0, where p is a polynomial. I mean one equation in one variable. That's. I mean one variable system is really one polynomial in one variable, one exponential polynomial in one variable. So you can force a solution to this one while keeping e increasing on the real line, and on the rest of the x1. No, but this is on an algebraically closed field. So you have also cosine and sine. Okay, I mean this is not a real line with where this function. I mean I think that was the misunderstanding.
The fixed field is real close.
Yes, yes, yes. The fixed field, yes. And you get solution to these ones, to this.
More questions?
Oh, yes, yes, yes. Yes, yes, with the Shannon property, yes. I mean, it's really all the properties except for, well, also the countable closure property probably doesn't work in the general case. But the Shannon property is there, yes.